Hello, dear students. I am Professor Ronindra Das from Achievers, and welcome to my lecture series on chemical equilibrium. So, the very first topic in chemical equilibrium is equilibrium in physical processes. And here we'll be discussing the concepts of phase transition. Now, what is phase transition all about? We are acquainted with the very fundamental phases like solid, liquid, and vapor. Even there are other phases as well, but I'll not be going into that in this particular lecture. So we'll confine ourselves to the three fundamental phases, that is solid, liquid, and vapor. And what is transition? Transition is moving from solid to liquid, from liquid to vapor, or directly moving from solid to vapor, or the reverse processes. These are called transitions. Now, what happens during phase transition? What happens during phase transition? We all know that during a particular phase transition, say water is converted into water vapor. So, this is a phase transition. So, we know that during the process of phase transition, the pressure and temperature has to be affixed. So, let us affix the pressure at 1 atmosphere and the temperature at the boiling point of water at 1 atmosphere, that is 100 degrees centigrade or 373 Kelvin. So, we have affixed the pressure at 1 atmosphere and temperature at 373 Kelvin. Now, what happens? The temperature and pressure will remain constant unless and until the entire liquid, that is water, is converted into water vapor. So, we are supplying heat to the system, and even if we are supplying heat to the system, there is no change in temperature. There is no rise in temperature. The temperature is going to remain constant at its boiling point at the defined pressure unless and until the entire mass of liquid gets converted into vapor. So, where does this heat go? It doesn't increase the temperature. Then where does this heat go? Actually, this is the concept of latent heat. I think we are all acquainted with this term. What does latent heat do? Latent heat basically makes a transformation of the molecular orientations. I mean to say, in liquid state, the molecules are relatively closely associated with respect to each other in comparison to that of the vapor state. In vapor state, the molecules are far away from each other. So, naturally, the molecular kinetic energy of the vapor state is much higher in comparison to that of the liquid state. So, the heat that we are providing, that is the latent heat of vaporization, that which we are providing over here, doesn't increase the temperature, but it basically transforms the orientation from liquid state to that of the vapor state, transforms the molecular orientation. It increases the intermolecular space, and thereby a liquid state of a particular matter is converted into the corresponding vapor state. So, this is what latent heat is all about. Okay. So, similarly, any phase transition will work in the similar fashion. I think these concepts are really there in your mind. If you have not registered that properly, then you need to go through this study material once again. Then I think you will all understand what I have told. Now, what happens during phase equilibrium or phase transition? Basically, I have told equilibrium. Basically, what happens, you see, when a solid is converted to liquid, then at constant temperature and pressure there will be an equilibrium between the solid and liquid phases. This pressure is constant and the temperature is obviously the melting point. It is also constant unless and until the entire process is carried out. Okay. Similarly, at constant temperature pressure, there will be an equilibrium between liquid and vapor. Similarly, at constant temperature and pressure, there may be an equilibrium between solid and vapor. All these three are phase equilibrium, where phase transition is taking place. Here you have affixed the pressure. Say you have affixed the pressure at 1 atmosphere, then this particular temperature refers to the melting point or freezing point. This particular temperature refers to the boiling point, and this particular temperature refers to the sublimation point. Okay. So these components are at equilibrium during the phase transition. So during phase transition, these components are at equilibrium. Now, if these components are at equilibrium, then what is happening? At equilibrium, what happens? At equilibrium, the rate of forward reaction is equal to the rate of backward reaction, or the rate of forward process is equal to the rate of backward process. And thereby, what happens? The amount of each of the phases will remain constant. The amount of each of the phases will remain constant. What I mean to say I am considering this particular example. So, if solid and liquid are at their equilibrium, then the rate of the forward reaction becomes equal to rate of the backward reaction, or rate of the forward process becomes equal to rate of the backward process at equilibrium. If this happens, then the rate of formation of the liquid phase is exactly equal to the rate of formation of the solid phase. That means the amount of the liquid and solid phases present at this particular phase equilibrium will be fixed. That means mass of liquid at equilibrium, this becomes fixed, and mass of solid at equilibrium, this also becomes fixed. Yet the process goes on happening. I mean, the conversion is continuous. Solid is being converted into liquid and liquid is coming back to solid. So this process is perpetual. It is continuous. It is happening continually. So I can say that rate of the forward process becomes equal to that of the backward process. So if this happens then obviously if you apply the basic logic, then you can say that once this condition is attained, then obviously the amount of liquid present at the particular phase equilibrium will become fixed, and similarly the amount of solid present at that particular phase equilibrium will also become fixed. but the process doesn't stop. Apparently, it seems that the process has stopped. The amount of liquid has got fixed, the amount of solid has got fixed. Apparently, it seems that the process has stopped, but the process happens continuously. So, it's a dynamic process. So, this is a dynamic process. And this funda is applicable for liquid vapor equilibrium and solid vapor equilibrium as well. Okay. So this is very simple. So this is very simple. We have understood. We have understood the nuances of phase equilibrium over here. Now let's continue. Now, here one important thing has to be noted. The Clapeyron Clapeyron equation. The Clausius-Clapeyron equation. Okay. So for that purpose, let us consider a general phase equilibrium. Let us consider a general phase equilibrium. So Q in equilibrium to R. Okay. What I am going to do over here is, I am going to relate in Clausius-Clapeyron equation, I am going to correlate equilibrium temperature with equilibrium pressure. Okay. So this is our objective. Now, let us consider two equilibrium conditions. So at first equilibrium condition, let us assume that the equilibrium temperature is T dash and the equilibrium pressure be P dash. Let's consider that. Here obviously delta G is 0. At equilibrium delta G is 0. That means GQ should be equal to GR. Let us call GQ as GQ dash and GQR as and GR as GR dash. Okay. And at second equilibrium condition, Let us assume TE to be T dash plus dt and PE to be P dash plus dP. Okay. Let us call this temperature as T double dash and P double dash. I have told that equilibrium is attained at a particular pressure and a particular temperature. So for water, getting converted into water vapor, the standard equilibrium is 1 atmosphere pressure 100 degrees centigrade. If the pressure is say 1.5 atmosphere, then the temperature is not 100 degrees centigrade, it is somewhere else, say 110 degrees centigrade. So what happens? If we change the equilibrium pressure, the equilibrium temperature also changes. So here, in this particular case, for Clausius-Clapeyron equation, we'll relate how the equilibrium temperature changes with equilibrium pressure. So under this condition, let's say GQ to be GQ double dash and GR to be GR double dash. So these are the two equilibrium conditions. These are the two different equilibrium conditions. Okay. So these are the two different equilibrium conditions. But for both the conditions, the common feature is temperature and pressure are constant and delta G is equal to 0 at equilibrium. So this is maintained. This is the common feature, but the values are different. Now let us subtract equation 1 from equation 2. Means GQ double dash minus GQ dash equal to GR double dash minus GR dash. So you can call it dg of Q equal to dg of R. Okay. Now we have got dg of Q equal to dg of R. Now we all know that for reversible process with no non-mechanical work, what I have got? I have got dg equal to VdP minus SdT. Okay. So let us substitute that. This is V of Q dP minus S of Q dt. This is V of R dP minus S of R dt. We applied the same form, VdP minus SdT. Now let us bring the VdP terms together and SdT terms together. So VQ minus VR, or rather write it in this manner, bring the SR term over here, SR minus SQ whole multiplied by dt equal to Vr minus Vq whole multiplied by dp. Why I am writing in this manner? Because our final state is R and our initial state is Q. So, for any change, we have to subtract the corresponding value of Q from the corresponding value of R. That will refer to a change. So, SR minus SQ refers to delta S and VR minus VQ refers to delta V. So, from here one can write dB dt equal to delta S by delta V. Okay. So, let us name this as equation number 3. Now, everything is occurring at equilibrium. So, again, at equilibrium, we all know that delta G equal to delta H minus T delta S, that must be equal to 0. Because this is the interpretation happening at equilibrium, because we have started with two different equilibrium conditions, first and second equilibrium conditions. So, the entire interpretation is being made at the state of equilibrium. So, you can apply the conditions of equilibrium. So, I have applied the conditions of equilibrium, delta G equal to delta H minus T delta S over here, and that must be equal to 0. That means delta S is delta H by T. From here we can find out this equation. So, this is equation number 4. Now, if you plug in the expression of delta S in equation 3, then what you are getting? Therefore, combining 3 and 4, what we are getting? We are getting dP dt to be equal to delta H by T delta V. This is the Clapeyron equation. This is the Clapeyron equation. Okay. Now, this Clapeyron equation needs to be modified to Clausius-Clapeyron equation. For that purpose, so let us write the Clapeyron equation once again. dP dt equal to delta H by T delta V. That's what we have already done. Now, you see, for solid being converted to vapor or liquid being converted to vapor, for these two equilibrium, where the final phase R is always vapor and the initial phase Q is either solid or liquid. For these cases, what is the expression of delta V? Delta V is V of vapor minus V of solid, or delta V is V of vapor minus V of liquid. For these two cases, the common feature is that the final phase is vapor. So, delta V is volume of vapor minus volume of solid, either it's volume of vapor minus volume of solid for the process of sublimation, or it's volume of vapor minus volume of liquid for the process of boiling. Now, volume of vapor is much greater than volume of solid or volume of liquid. So, for both these cases, delta V is almost equal to volume of vapor. Okay. And volume of vapor is nRT by P. Considering ideal vapor, we have considered ideal vapor. Now, if you plug in this particular expression nRT by P in place of delta V, what do you get? You get dPdt to be equal to delta H by T multiplied by nRT by P. Now, delta H by N is the change in enthalpy per unit total number of moles. That is nothing but the molar change in enthalpy delta H bar. This P goes to the numerator divided by RT square. Now you bring this P to the left hand side. So 1 by P dPdt equal to delta H bar by RT square. Now we all know that dx by x is basically dln x. We all know this from calculus. So dp by p, this is replaced by dln p. So you get dln p dt equal to delta H bar by RT square. So this is the expression. Okay. And this is the modified Clapeyron equation, and this is known as Clausius-Clapeyron equation. So Clapeyron equation is the more general equation. This is valid for any phase transition, and this is valid for phase transitions where you are ending up in the final vapor phase. Okay. So this is all about the Clausius-Clapeyron equation. And students, the cases of dissolution of solid and gases in liquid, this particular topic is absolutely an informative topic. Everything is there in your study material. So there is nothing to understand over here. This is very simple. You have already done this in your secondary level. You just go through this material, you'll understand these things. So the process of dissolution is very simple. You'll understand this thing. Only one important concept has to be taught over here in terms of the process of dissolution, and that is Henry's law. This is very important. Other than Henry's law, everything is very informative. So I am not going to teach all that things over here because this is very informative. You can directly understand that from the study material provided itself. Okay. So let's move on to the Henry's law. This is very important. Henry's law. So let us ponder on the statement at first. What the statement is saying? It states that the mass of gas that dissolved in a given mass of solvent at any temperature is proportional to the pressure of the gas above the surface of the solvent. That means you have a liquid solvent over here. The solvent is at its liquid state, and the solute is gaseous. Okay. And you have covered this. So these are the gas molecules present over here. Now they are saying that you are provided with this particular system where the solvent is at its liquid state and the solute is at its gaseous state or vapor state, and you have kept the temperature constant. Now they are saying that the mass of the gas that will get dissolved in this liquid solvent is directly proportional to the superincumbent pressure of the gas over the liquid. So mass of the gaseous substance or gaseous solute that is getting dissolved in the liquid solvent is directly proportional to the superincumbent pressure. And obviously m should be equal to k multiplied by p. This k is the proportionality constant. And this proportionality constant, it depends on temperature, because you have kept temperature constant all throughout the process. So naturally, under the constraint of constant temperature, you are getting k to be equal to the proportionality constant. So k must be a function of temperature, and k also depends on the nature of solute and solvent. So at a particular temperature, if we affix a temperature, then K determines the property of this particular system. You see, if we plot M with respect to K, then what will you get? You see, y equal to mx type of equation. Here y is m is k, and x is p. So you will get y equal to mx type of equation, and that is a straight line satisfying the origin. It will not go into any other quadrant because neither m nor p can be negative. And the slope of this is k. And this slope k will be different for different systems. Temperature is kept constant. We are not varying the temperature. Okay. So under the constraint of constant temperature, k, that is the positive slope, k is always positive, but the value of the slope will be different for different systems. As I have told that, if you affix the temperature, then k is basically the property of the concerned system. So k will be different for different systems. So k will vary for different systems even if you affix the temperature. Now if a particular gas is very much soluble in a particular solvent, then the proportionality constant k will be much higher. And on the other hand, if a gas is not that much soluble in a particular solvent, then the value of k will be lower. Even it is positive, the value will be lower. So that's what is reflected over here. You have taken water as the common solvent, and you have affixed a temperature. Now you have taken three different solutes: oxygen, nitrogen and helium. As oxygen is much more soluble in water in comparison to nitrogen and helium, the slope is highest. Now nitrogen is also soluble in water to some extent. Obviously, the solubility is lower than oxygen but greater than helium. That's why the slope is at the middle of oxygen and helium. And since helium is of lowest solubility, the slope is least. So I think you all have understood this. So this is all about our first part of chemical equilibrium. So thank you and bye bye for now.